A conditional probability occurs when we have some information which restricts the possible outcomes of a system. Mathematically, if we have two events E and F, and we know that F has already occurred, how does this affect the probability that E will occur? To derive the formula, it's best if we draw a picture. Let's draw the two events E and F so that they overlap. We know that F has already happened, so we can restrict our attention to just F. Now within F, we want to know what the likelihood is that E also happened. The probability of E given F, where here we can think of this little vertical line as being the word given, is the space in both E and F divided by the space in F. It's the double-hatched area divided by the single-hatched area. As an example, let's return to our classic 2-fair D6 scenario. Let's let E be the event one of the dice rolls is a 4, and F is the event that the sum of the values is 10. Let's find the conditional probabilities of E given F and F given E. Now, as usual, I'm going to draw out a roll table, only this time I'm going to put the sum of the dice rolls into the table. So this is going to take a second, just hold on. Let's start with the probability of E given F. What we're asking for here is the probability that a 4 is rolled if we already know that the sum of the dice is equal to 10. So I'm going to repeat the formula here just so that you can see it in front of you. And in the table, I'm first going to highlight F, since we've already assumed that F has happened. Note that the assumption that F has already occurred has really limited the number of possible rolls which possibly could have happened. Now let's put a star on those outcomes whose roll include a 4, of which we can see that there are 2 of them. If we plug everything into our formulas, we get an answer of 2/3 out. Now for the probability of F given E, which is the statement that, the sum of our dice is 10, given that we rolled a 4, only the denominator has changed. Let me highlight those outcomes corresponding to E in red here. The start outcomes are still those of E intersect F. And if we work out all those numbers, we can get an answer of 2/11 out. Now something special happens when E and F are independent. In that case, we know that the probability of E intersect F is just the probabilities of E and F multiplied together. Putting that into our conditional probability formula causes the probability of F terms to cancel, giving just the probability of E. And yeah, that intuitively makes perfect sense. Because if E and F are independent, then the outcome of E does not depend on whether or not F happened, and so the conditional probability of E should just be the probability of E. Moreover, let's take a closer look at our formula. By rearranging the terms, we can solve for the conditional probability of E and F in terms of the conditional probability. And, moreover, the symmetry of the argument means that we can interchange the roles of E and F to get a similar equation. Both are valid. The thing is, this isn't new, right? We've been doing this secretly the entire time. If you go back and you check out the independent events video, we gave a non-independent example wherein a bag was filled with 2 black and 2 white balls. In that video, we were asked to determine the probability that both balls were the same color, but let's just focus on the special case where both balls are black. Let's define 2 events, one for each draw. E will be that the first draw is black, while F is that the second draw is black. What we're looking for is the probability that both balls are black, so E intersect F. By our discussion above, this can be computed by using the conditional probability as follows. Here I'm doing the probability of F given E just because it makes more sense chronologically to ask that the probability that the second ball is black knowing that the first draw was black. Okay, let's draw out our 2 scenarios, remembering that we're not replacing the balls. In the first draw, the probability of a black ball is just a half. We can see that easily. But in setting up the second bag, which now only has 1 black ball, we've assumed that E has already happened, namely that we've removed a black ball. So the probability of F here depends on whether or not E has happened. In this situation, it's not too hard to see that the conditional probability is 1/3. And we can take all of that and plug it back into our formula and arrive at the same answer we did in the previous video, which is 1/6.